Okay, so let's start today's class. Good morning, everyone. Okay, so I can find many popular receipts here. Uh, so actually, when during the class re-registration period, many students sent email me because they wanted to take this course, but we have we don't have the available seats here. But now I can find many available seats. Okay, so uh, so actually we've taken nearly one month of this course, right? So because it is the late March. Okay, so I hope everyone keeps working hard for this course until the end of this semester. Okay. Okay, so I will briefly review what we learned in the previous class. So what did we learn? So actually, in the previous class, we learned about the power consumption of the digital circuits. So you may think that so we are learning about the hardware topics of the computer systems. So which means I mentioned that the hardware works in the real world. So actually the hardware consumes electric power and electric energy. So that's why our smartphone have batteries. Okay? And then if the batteries are consumed the earth, that we cannot run our hardware, right? Because our hardware consume electric power. And then we learn how to calculate, how to estimate the electric power consumption. So we actually there are two kinds of power consumption: the dynamic power and static power. Okay, and then actually we can calculate the dynamic power when the input and output signals of this circuit changes. Okay, so which means these are the examples of electric signals. So actually, it's not a real waveform. It's very clear, right? But actually, real electric signals are very nasty. But we think that every signals have one and zeros. Okay, 1 and 0 are repeated. So when the signals are changed, so we already learned how to implement the basic CMOS circuit like this. So we can implement the CMOS circuits by using PMOS transistors and NMOS transistors, right? And then if input signal values are changing, then output signals can be also changed. So when the signals are changed, then electric charge transfers through this network. So this circuit consumes dynamic power. Okay. Also, I mentioned the static power. So it is because actually, we can think that if both transistors are controllable switch. So controllable switch. So which means that the drain and source nodes can be connected or disconnected based on the gate signal. Okay, but I also mentioned that these are not ideal devices. It's not a perfect switch. Okay, so even though these transistors are off, the electric currents can flow through VDD to ground. Okay, because we can actually there are no ideal devices in the world. Okay, so static powers are also consumed in our electric devices. Okay, this is the example. And then So in the previous class, we learned about the basic combinational circuits. Okay. So when the combinational circuit is defined, we can define input signals and output signals, and then functional specification, the functional behavior of these digital circuits. Also, we can define timing specification. Okay, so I mentioned that this is our hardware system. So when our hardware system works, then time is taken. Okay, so you can think that this is just a black box. So input is given to the system, and this system generate outputs based on the functional specification. Okay, but after some delays. Okay, after some time. Okay, so when the digital system is defined, we can define these factors: inputs, outputs, and the functional specification and timing specification. Okay, so we learned about the combinational circuit. Okay, so these are the rules of combinational composition. So if combinational circuits meet these conditions or these rules, so we can say, oh, this is a combinational circuit. Okay. Okay, so and then Boolean equation is just similar to our normal equation, but Boolean equation just handles true or false. Okay, that's why Boolean equations are simpler than our normal equations or normal algebra. Okay, and then we learned about the sum of products. Okay, so then why do we know how to implement sum of products? Okay, so you can start from the truth table. So what is the truth table? Truth table defines the all possible digital inputs, and then also in the truth table, these outputs are defined based on the input digital signals. Okay, so as you can see, this digital system has two inputs, two digital inputs. So we can define 4 cases using two inputs, two digital inputs. And also we can define the output of this system based on the inputs. So firstly, we can define the truth table of a digital system. Then, what is the sum of product? So product means the multiplication of the two variables, and then I believe you already know about the sum. So sum of products is something like this: A, B plus B, C plus C, D, Y, O. So we can find products here. Also, we can find sum here. So what you need to know that these are real multiplication. These are not real multiplication. Also, these are not real addition, right? Because this means and, this means this means and then this means or, right? Okay, so we can think that the sum of a product form, SOP form, is the implementation form of the and or of and, because I said that the English is the order of the English term is the inverse of the Korean term. So the or of and, okay. So which means we need to use the mean term, okay, to generate the SOP form from the truth table. And when we generate SOP form from the truth table, then we need to focus on how to generate output 1 from mean terms. Okay, so you can understand like this. So y is the some product or product. Then how can we make y 1? Is I think I mentioned that these are ors. Okay, so how can we make if this is 1 or if this is 1 or if this is 1, then y becomes 1. So that's why we focus on how to make y 1, okay, using main terms. Then how can we make this y 1 using main terms? Okay, so in this truth table, if a is 0 and b is 1, then y becomes 1. Then how can we make y 1? So if we just add a bar and b, okay, a bar and b, then we can make y 1. Right. And then another midterm. So this is another output, y equal 1. So if a is 1 and b is 1, then y becomes 1. So in the sum of product form, I mentioned, oh, this is 1, or this is 1, or this is 1. So which means if this term is 1, or this term is 1, then y becomes 1. So the sum of product form, if by combining main terms and then ORing main terms, they can make y 1, and we can implement Boolean equation that meets the functional specification of this truth table. Okay, so using the SOP form, so we can make Boolean equation that can meet the functional specification of this truth table. Okay, you understand? But I believe that you can easily understand how to generate the SOP form. Why? So it's straightforward. So actually, we can just select the rows that can make y 1. So there are 2 rows in this example, and then we can actually figure out mean terms that can make y 1, right? Then we can just add these mean terms. And then that's it. This is the sum of product form. Then we can think about the this is another sum of product form. So we can think about the product of sum form. Okay. So what is the product? What is the product of sum form? Sum form. So it's easy. So if you see that this terminology, then you can think that, oh, it's the sums. So because the order of English terminology is the inverse of the Korean. So firstly, we can think about the sums. What are sums? It's the ordering of input signals, right? So we can think about the sum or like A plus B or B plus C, and like that. These are sums of the input signals. Then if we just multiply these terms, so like this, then we can generate the product of sums, right? So product of sums. Then like the sum of product form, the SOP forms, then we can also generate the product of sums based on the truth table. Okay, but it's not straightforward as sum of product form y. So you can think like this. So y equal a multiply b multiply c. Then how can you make? So you can think like this. How can you make y 1, but the value of y as 1 using these terms a, b, c. So these are ands, right? So if all digital values of a and b and c are 1s, then we can make y 1, right? So it should be 1, 1, 1. So which means in order to generate product of sums from the truth table, then in order to make y as 1, then we need to make all terms 1s. So output of these terms as 1. Then, unlike the SOP form, then we need to focus on the next terms that can make y 0. So this is, you can think inversely. When you generate the POS form, we need to focus on this row that can make y 0. Okay. Then if you see the next term of this row, then you can think that, oh, this variable. So if a is 0 and then b is 0, then y becomes 0. Okay. So what is different? So in the SOP form, in order to make y 1, we need to focus on this term. So which means that in this truth table, then if a equals 0 and b equals 1, then y becomes 1. So in order to make y 1, then we need to multiply and a bar and b. Okay. So using the main term, then we can make this y 1. Then in the POS form, I think I mentioned that we need to focus on the next term that can make y 0. Okay, so how can you make y 0 using this next term? So a should be 0 and then b should be 0, right? So this next term is the a plus b, right? And then another, we can find another row that can make y 0 here. So which means that a is 1 and b is 0. Then for this max term, then in order to make y 0, right? Then a should be 1. So which means the max term for this row should be a bar. Or right. So if the b is 0 and then a bar is 0, which means that a is 1, right? So a bar or b becomes 0. So we can find the two rows that can make y 0s. So like a or b, a plus b, and a bar plus b. And then we can just multiply these two terms. Then this is the POS form of this truth table. Okay, so in order to generate the POS form from the truth table, we need to think inversely. So actually, I said that so in order to generate the SOP form from this truth table, then we can think straightforwardly. So which means that we can find some rows that can make y 1, and by combining these min terms that can make y 1, then we can generate the sum of product form from the truth table. But in order to generate the POS form from the truth table, then we need to focus on the next term that can make y 0. And then by multiplying these next terms, then we can generate output y based on this truth table. Okay, so which means, in order to generate SOP form, we need to find the mean term that can make output 1. And then in order to generate POS form from the truth table, we need to find the next term that can make y 0. Why? Why? It is because of properties of AND gate and OR gate, right? So how can we generate y is 0 from some AND A and B and C? Okay, how can you make y 0? So actually, we need not to generate the POS form. We focus on how to make y 0. Okay, you need to know. You need to understand this. So POS form. So how to make y 0? Okay. So in order to make y 0 using the A and B and C, then you can think one of these terms need to be 0, right? So you can think inversely. So when I explained about the sum of product form, then in order to make y 1, then this is the A or B or C. So one of these terms need to be 1, right? So it's the same, right? Actually same. In order to make y 0, then one of these terms need to be 0, right? Actually the same. What is different? Only 1 and 0. That's why when we generate the product of sum, then we need to figure out the rows that can make y 0. Understand? So actually I believe you can easily understand how to generate sum of a product form. It's because you can just focus on one. So usually the common people just focus on how to generate the 1 or how to generate 2 from the digital logic. Then, and as I mentioned, in order to generate the output 1, then SOP form, these terms can be 1 or 1 or 1. Okay, and then we can think inversely. In order to make y equals 0 from A and B and C, then it should be O. Then we need to make A is 0 or B is 0 or C is 0. Okay, you understand? So we can generate the POS form like this. Okay, so in summary, in this truth table, we can just find the row that can make y 0 here. Then we can figure out next term that can make y 0. Okay. Then by multiplying this next term, then we can generate POS form from this truth table. Okay. I hope everyone can understand. Okay. Then let's think about the examples of Boolean equations from the real example, the real world example. Okay. So as I mentioned, the Boolean actually in the real world, we just use decimal numbers, and so which means that we use the equations that equations that use decimal numbers. Okay, but Boolean equation is different because the Boolean equations just use variables that have only two values, true or false. Okay, but we can generate any Boolean equations from our real world examples. Okay, so this is the example. So you are going to the cafeteria for lunch, so I think you can have lunch after this class. So you want to eat lunch. So this is the result. So actually you have a true and false result. So which means you want to eat lunch. So which means that E equals 0. So E means eat. And then what? Which condition? If the cafeteria is not clean, so C is clean. So this is the term, the variable. So if the cafeteria is not clean, then C equals 0. And then if they only serve meatloaf, so some kind of meat, then M equals 1. So M means the meat. So using this condition, we can generate truth table like this. So E is the result of this system. Okay, so which means that you can eat a lunch or not. So if E equals 1, then which means that you will eat lunch. Okay, based on some conditions, which means if the cafeteria is clean or not. So if the cafeteria is clean, so which means C equals 1. If not, C equals 0. And then if the menu is meatloaf, then M becomes 1. So there are two conditions, and then as you can see, so we can define the result of a condition as true or false. Okay, there are only two cases for each condition. And then by combining these conditions, we can generate output E. So you will eat the lunch if the cafeteria is clean and the menu. Okay. So you will not lunch. Okay, you will not lunch. Then which means that if the menu does not have meat, okay, 0. The cafeteria is clean, and then if the menu is not meatloaf, is 0, then you will eat. Otherwise, you will not eat. Okay. So based on these conditions, then you can generate truth table like this. So why did I explain like this? So this is the hardware. So which means that actually we need to generate the hardware that can meet the specification of our result. Okay. So, but based on our real examples, so our some real variables or real inputs, then we can define the output of a system, of how the system is. Okay, so which means that we can generate a truth table. Okay, then based on the truth table, we learn how to implement SOP form and POS form of the Boolean equation. Then, which means if we can generate the truth table, then we can implement Boolean equations from the generated truth table, which means we can build a data system that meet the conditions of this example. Okay, using the real world examples. Okay, so as I mentioned, we can implement Boolean equations as the SOP forms, SOP as a SOP form or POS form. Okay, So this is the same truth table. In order to generate the SOP form, then I said we need to focus on the output one, which means that we need to use the min terms that can make y ones. Okay, so actually there are only one row that can make y one, so which means each y equal c and m bar. Okay, so this is the Boolean equation of this truth table. Then how can you make a POS form of this truth table? So we can observe 3 rows. They can make output 0. Okay, and then we can figure out max terms for each row. Okay, here. So this is the max, the low, and it's the low that can make y zeros. And then by combining these max terms, like so y equal c and m, c or m, c plus m, and multiply c plus m bar, and then multiply c bar plus m bar. Okay, we can generate POS form like this from this truth table. So based on the truth table, so we can generate Boolean equations. And then the Boolean equations just use or plus and add. So and okay. So which means, so actually in the previous class, we learned how to implement basic gates, right? So we learned how to implement AND gate and how to implement OR gate. So what does that mean? If we can generate Boolean equations, then we can implement basic digital system using basic logic gates, okay, like AND gate and OR gate, right? Do you understand? Okay. So this is the answer. And then this is another example. So we will go to the farm and please the output. If it's not raining and we have sandwich. Okay, then how can you generate the Boolean equation from this example? So actually, we can think straightforwardly. So actually, it's very easy. So that's why I mentioned that the SOP form is more straightforward, and then it's easier to understand. Actually, using this sentence, we can directly generate Boolean equations, right? Why? How? So P is R bar and S, right? So if you read this sentence, the P is the output, and if it's not raining, it's not raining, so which means not raining, R bar, and it also AND gate in the circuit, and then we have sandwich. So if we cannot find any not in this sentence, so actually which means P equal R bar and S. Okay, but in order to generate the POS form, then we need to generate the truth table from this sentence. We need to then from this truth table, then we need to generate the POS form. Okay, so okay. So another example. So it's also simple. Okay. Okay. So until now, we learned how to implement Boolean equations from truth table. So I mentioned that from the real world example. So real world example. So actually in the real world example, in order to generate some outputs like true or false outputs, then we can define some conditions. Okay, the conditions are inputs of this system. So using this real example or real situations, then we can define truth table. Okay, and then based on the generated truth table, we can generate Boolean equations. So there are two possible forms, SOP forms or POS forms. Okay, and then we learn how to implement Boolean equations like POS or SOP forms from the truth table. Okay, and then now we will learn about Boolean algebra. So what is Boolean algebra? So we learn how to generate the Boolean equation like from using SOP or POS form. But what's the problem? It is not optimized. What does that mean? It's something like this. So what is the real algebra using the real world algebra? Like the y equals a plus b, c plus b, and then e plus f. Something like that. So we may think like, it's not, who knows? Like 2a plus 2b, 3c plus d, 4e plus f. So we can write real algebra like this, but this is not optimized. Right. So there are 6 terms here, right? There are 6 inputs, 6 terms that they will have. But this equation is not optimized. It's not a short form. So it's the same to the Boolean equation. So we learn how to generate Boolean equations using SOP or POS forms. But these Boolean equations are not optimized. Okay, so which means we can generate simpler Boolean equation from the truth table. But when the firstly SOP or POS forms are generated, these equations are not optimized. So we will learn how to optimize Boolean equations using some axioms and theorems. Okay, this is the Boolean algebra. But the Boolean algebra is much simpler than the real algebra, because as I mentioned, the Boolean equation is just handle true or false, the 1, 1, 0. So which means actually the Boolean algebra is much simpler than real algebra. So the real algebra is a very difficult, right? Okay, so you can find 2 terms like axioms and theorems. So you may think that axioms is a new terminology. So what is the meaning of the axiom? The axiom means actually a statement accepted as true. So which means it's obviously true. So we don't need to prove that this term is true. We don't need to prove if this term is true or not. Okay. So if a statement is obviously true, then this statement is an axiom. Okay, it's an axiom. But theorem is a little bit different. We can prove some theorems based on axioms. Okay. So let's see the axioms of Boolean algebra. So this is the axiom numbers, and then these are axioms. So as I mentioned, axioms are obviously true. So we don't need to prove. So, for example, the axiom number 1, the b equals 0 if b is not 1. It's obviously, right? It's obvious. Actually, we are learning about the signals or the systems. Actually, we are learning about the Boolean equation. Then each term of the Boolean equations have only two values, 1 and 0. Obviously, b is 1 if b is not, b is 0 if b is not 1, right? It's obviously. And then inverse of 0 is 1, it's also obvious. And then 0 and 0 equal 0, right? The 1 and 1 equal 1, then 1 and 1 and 1 equal 1, and then 0 and 1 equal 0. Okay? Actually, these three laws just to define the definition of and OR gate. Okay, and this is the NOT, and it's just the first law just defines for binary field. Okay, actually, each term has only two values, two possible values. So we don't need to prove, because it's just obvious. And then we can find dual of the each axiom. Okay. So dual means that, so actually there's the duality in axiom and theorem. So as actually in a Boolean equation, the values have 1 and zeros and ones. Okay, there are only two values. So which means if we define axioms or theorems for only 0, then we can define another type of axioms for value 1. Okay, that's why the axioms and theorems have duals. Also, and OR gates. So if we define some theorem or axiom for AND operation, then we can define the OR operation. So the similar axioms or theorems for OR operations. So these are called, this is called duality. Okay, let's see the dual of these axioms. It's also obvious, right? So if p equal 1, if p is not 0, then it's not. Definition of not also it defines the properties of OR operation. 1 or 1 plus 1 equal 1. So which means 1 or 1 equal 1, right? And then 0 or 0 equal 0. So obviously, and then 1 or 0 is equal to 0 or 1 or 1. It defines just the, so actually these parts just define the AND operations. Also, this part just define the OR operation, right? Okay, and then let's think about the some theorems of Boolean algebra. Okay, actually these theorems are also very simple. I believe we don't need to prove. Okay, so these are theorem numbers, and then these are theorems. Okay, then let's see some theorems of Boolean algebra. B and 1 equal B, right? Why? Why? So we can prove like this: if B equal 1, then 1 and 1 equal 1. And then if B equals 0, and then 0 and 1 equal 0, right? So if this term is 1, and then this is the AND operation, then the B and 1 is a B, obviously. And then also B and 0 equal 0, right? So this is called the identity, and then this is null element. And then B and B equal B. It's also obvious, right? So 1 and 1 equal 1, 1, 0, and 0 equals 0. So which means B equal B is B. Now B and B equal B. And then inverse of the inverse is the same. So it's a B inverse B bar of B bar. The inversion of B bar is B, okay? And then B and the B bar equal 0. It's also obvious, which means, so if this is 1, then this will become, it will be 0, it's a 0, and this will be 1. So 1 and 0 equal 0. The complement. Also, we can find the dual of these theorems, right? So identity, so B and 1 equal B, then dual of this theorem is B or 0 equal B. Obviously, right? Right. And then P or 1 equal 1. Okay. So it means if we just use 1 for the one of input of the OR gate, then it will always generate 1, right? That's so easy, right? So P or B is the P, and then so there is no dual here, and then P or P bar equal 1. Okay, because if we use the P bar, the one of these terms will be 1. Okay? So that's the identity theorem. Actually, it's very obvious, right? I hope it's obvious, right? So this is the AND gate, and then one of input is 1, and it's same to the B. The one of input is 0, and then we use the OR gate, and it's also same to B. And then also this is obvious. So one of input is 0, and then it becomes 0. One of input is 1, and then this is the OR gate is 1. The same. So it's a B, the B. So and then if the NOT gates are connected serially like this, then it's same to B. Okay. Then also this is 0, and this is 1. Okay. Okay. Until now, this is very obvious. These theorems are obvious. So we can think about some a little bit more complex theorems like this. So which means these theorems just handle two different variables. Okay, so as you can see, this column is the theorem number. Then some theorems are defined. So we can define dual of a certain theorem. Okay, let's see the first theorem. B and C equal C and B. It's called the commutativity. Well, in Korean, it's 교환법칙, 맞죠? But it's obviously true, right? As you can see, so AND gate has two inputs, but actually the value of the AND gate is not the value, the output of the AND gate does not depend on the order of inputs, right? So which means the B and C equals C and B. It's also same to the OR gate. The output of OR gate does not depend on the orders of input signals. Then associativity. So actually, so it's also the same. The output of the AND gate does not depend on the order of inputs, which means that if we use 3 inputs, then we actually, if we can generate the first end of the 2 terms, it's the same to the first, actually, so the bracket of B and C and D equal B and bracket of C and D. Okay? Because as I mentioned, so you know, as I mentioned, you can understand that this is the product, is a kind of the very similar to the multiplication. And also you can say that, or this is the addition. Okay? But so actually the form is very similar to the normal algebra. Okay, So and then this theorem is called the associativity. In Korean, 법칙이라고 하나요? Okay, so this theorem is called the associativity. And then let's see the TA. I believe you can easily understand this theorem. Okay. Actually, it's the same to our real algebra. How about this one? A little bit different. Okay. So we can actually B multiply C plus D equal B multiply C plus B multiply D. And then this theorem is called the distributivity. Then in Korean, right? We can find the distributivity for this OR gate and AND gate like this. So I believe you can easily understand this equation. Right? It's the same to the real algebra, but this equation is different. Why? Why did this different from the real algebra? So it is because this is not real addition. This is just OR gate. It's not addition, okay? So that's why so if you see the AND gate and OR gate, so these are just gates. Okay? We just define the output of AND gate from two inputs and then output of OR gate from inputs. Right. So which means actually B multiply C plus D, it can be, it's like C, D, and then D. It can be implemented like this. Okay? So we can use OR gate and then we can use AND gate to implement this equation. Okay, so and then so actually this equation can be rewritten like this. So if we rewrite this equation, then it looks like so it's the B and C and D, then AND gate first, and then it's the OR gate. And so actually these gates are just changed, but the form is the same. So you may easily understand this distributivity of and OR gate, but we can just apply the same distributivity for the AND and OR gate because these are just gate. Okay. So another theorem P9, P10, T11 for the covering and combining and consensus. So actually, we will prove this theorem later. Okay. Also, unlike the very basic theorems from T1 to T5, so we sometimes in order to understand how these theorems are true, then we need to prove that these theorems are actually true. Actually, there are two methods. The first method is the perfect induction. Then second method is that we can use the other theorems and the axioms to prove this theorem. So what is the perfect induction? The perfect induction is just actually we can define all possible inputs. But it's kind of dumb, right? Because so the first method is the perfect induction. So which means that we can define all possible inputs for each term, and then we can verify output of this Boolean equation. So you may think, oh, this method is very dumb because we need to define all possible cases. But this Boolean equation, it is we can use this perfect induction method because each term has only two possible values. So we can also apply the perfect induction. So it's also called the proof by exhaustion. Okay, let's see the T9. So I said, okay, until here, this is just a very simple theorem. These are simple theorems, but T9 is called the covering. It's a B and B plus C equal B. Then how can we prove this is true? The first method is the perfect induction, and the second method is we can use other theorems and axioms. Okay, then how can we apply the perfect induction? It's very easy because in this theorem, in this equation, there are two terms here, B and C, and then we can define B plus C, and then B and B plus C. Okay, it's kind of dumb method, but it is possible. What is B plus C? The B or C? The 0, 1, 1, 1, right? Then we can apply AND gate for B and B plus C. Then what is the B and B plus C? It's 0, 0, 1, 1. Then, as you can see, it's same to the B. Why? It's very easy because there are only 4 cases, okay, for this equation. Okay, the same. Then how can we apply the other theorems? We can apply like this. So so B and B plus C, then it is B and B and then B plus C. We can apply the distributivity, right? And then we know B and B is B, right? Then B and C. Okay? Because B and B is B, right? Okay, we can rewrite this term as the B and 1, right? Okay, then we can rewrite this equation like this. This is the inverse of distributivity, right? Because we can find A and B here. There's an N, there's a 1. So 1 plus C. What is 1 plus C? It's the 1 or C, which is 1. And then B and 1 is B. Okay. So by using other theorems and then other axioms, we can prove this covering theorem. Okay, like this. How about the combine? Actually, so we can also apply the distributivity. Okay. See, so by this combining, then we can apply the inverse of the distributivity, and then see. I think there is missing here. Oh, okay. Oh, it is missing. Oh, because I need to write some line above this C. Okay. Okay. This bar is missing. Okay. So this is bar. So B and C plus B and C bar. So and then by applying inverse of distributivity, the B becomes B bar. Okay, sorry about that. The bar is missing, and then C or C bar is equal to 1. The complements the other theorem, and then B and 1 equal B. So, okay, so it's to be here. Why is it missing? Okay, and then so we can apply some state. We can apply the same proof methods for the consensus theorem. But I want to introduce another important theorem. It's called the De Morgan theorem. It's very important actually. So I believe you can easily understand the other theorems like this, the commutativity and then associativity and then distributivity. And then also by using these simple theorems, then we can prove, oh, these theorems are true in Boolean equation or Boolean algebra. Okay. Axioms are very simple and then very easy to understand. And then also some theorems are also very simple. And then by using these simple theorems and the axioms, we can prove the other theorems. But this De Morgan theorem is very important theorem, the Boolean algebra. So what is the De Morgan theorem? So it's you can find the B and C and D, and then the bar. So what does that mean? It means, so it's the B, the B, C, D, and then this is the AND gate. It's the AND gate, and then it's the NOT gate. But this can be same to the B. So you can find the B bar here. So B, C, D. So NOT gate here, NOT gate here, NOT gate here, and then the OR gate. This is the De Morgan theorem. So actually, the entire AND gate, the product terms, if the inversion of the product term is the inversion of inputs and different gate, that is the De Morgan theorem. So what is changing? In this equation, the first the left side of the equation, and you can find that these are inputs, and then AND gate here, and then output of AND gate is inverted. Okay, and then this equation can be translated into the inversion of all inputs, and then the gate is changing. The AND gate is changed to the OR gate. Then that gate is removed. This is the De Morgan's theorem. So actually, this is the unique theorem of the Boolean algebra. Okay, so actually the previous theorem, like the commutativity, associativity, and distributivities are also common to the real algebra. But the Morgan theorem is only unique for the Boolean algebra. Also, the inverse is the same. So we can also define the dual of the Morgan theorem. So which means inversion of the B plus C plus D is equal to the inversion of all inputs, and the gate is changed. The OR gate is changed to the AND gate, and then AND gate is changed to the OR gate. So this is the Morgan theorem. So why is this so important? So I will explain later. Okay, about the Morgan theorem. Wait a second. I think I'm using the different one for the slide. So actually the slide is updated, you know. So I just I updated the posted slide on the platform. So so okay, let's see the Morgan theorem further. So actually, as I mentioned, so this is the definition of the De Morgan theorem, and then you can easily simply understand the De Morgan theorem like this. So using the two terms like the two inputs like A and B, the inverse of the A and B is equal to inverse of A or B. So using the basic logic gate, so we learned about the basic logic gate like this. So this is the NAND gate, and as you can see, this is the OR gate. And then I mentioned that bubble means the inversion. So it's a kind of inversion of the signal. So which means that, as you can see, this is actually NAND. Okay, so it's a NAND gate because we can find bubble at the output of the AND gate. So De Morgan theorem mentioned that this NAND gate can be changed into the inversion of inputs A, B, inversion of input, you can find bubble here, and OR gate. Okay. Also, we can also observe the same De Morgan theorem for the OR gate. So this, as you can see, this is the OR gate. Okay, so actually OR gate. And then, input is inverted like this, then gate is changing. Okay. So for the basic logic gate, you can understand the Morgan theorem like this. Okay. So which means so I mentioned that bubble is just the inversion. So if we can find bubble at the output of the basic logic gate, like AND gate or OR gate, so it's only applied to the AND and OR gates. So if we find a bubble at the output of the AND or OR gate here and here, okay, it's the same. Okay. Then we can move this bubble to the all inputs, okay, like this here and here. Then the gate is changing. So this, we can say that, oh, these gates are the same. Okay. Also, inverse is the same. So if we can find the bubble of the inputs here, then this bubble can be moved to the output of the gate. But gate is also changing. The OR gate is changing to the AND gate, and AND gate is changing to the OR gate. Okay, so this is the actually using the bubble and then these gates, then we can understand the Morgan theorem like this. Okay, so let's apply the Morgan theorem. Then what is the Boolean expression of this gate? So what is the Boolean equation actually? So y. So actually for this term, so this is the NAND gate. So y equal a plus r is an AND gate. Sorry. This a and b and bar. Right. Also, this is the another NAND gate. So it's a CD here, and then it's another bar is here. This is the Boolean equation of this gate. And then we can change this gate like this. What is changing? So if you see this NAND gate here, and then by applying the Morgan theorem, then this bubble is moved to the two inputs of this AND gate, right? And this gate is changed to the OR gate here. So what can you see? What can you observe? So bubble is here, and then bubble is here. What does that mean actually? It's like the bubble and bubble and bubble, bubble. So actually this is same. Inversion of inversion is the same. Okay. So actually, because two bubbles meet each other, that bubble disappears. Bubbles disappear, right? Two bubbles meet in the wire, bubbles disappear. So actually, okay, there is no bubble disappears, bubbles disappear. So we can just connect this line like this. So what does that mean? Actually, the y equal a e plus c. And then this gate is the y equal large inversion a e c. Okay, actually this is the same. So by applying, we can. So I explain. We can explain the Morgan theorem like bubble pushing. Okay, so which means that you can just push the bubble into the bubbles in the output and OR gate into the inputs of and OR gate, and then the gate is changing, also vice versa. Okay, so by applying the Morgan theorem, we can rewrite the Boolean equations like this. Okay. So, okay, so I will start here. So we learned about the Boolean algebra. So we learned about the Boolean theorems. Okay. So here, please understand these theorems. Okay. So, any question? Thank you for your attention. See you in the next class.